compound interest. Hello folks, my name is Rafael. I am an electrical engineer, and in this video I would like to have a conversation with you about compound interest, which is a very important subject for the fields of economics, engineering, energy markets, and commerce in general. Let's read the text and debate. Solving compound interest problems. What is compound interest? If you walk into a bank and open up a savings account, you will earn interest on the money you deposit in the bank. If the interest is calculated once a year, then the interest is called simple interest. If the interest is calculated more than once per year, it is then called compound interest. Let's see the formula. Compound interest formula. The mathematical formula for calculating compound interest depends on several factors. These factors include the amount of money deposited, called the principal, the annual interest rate in decimal form, the number of times the money is compounded per year, and the number of years the money is left in the bank. Okay, this is very important because this is a source of doubt for people. In decimal form, okay? We are going to see how to use these numbers. These factors lead to the formula FV is equal to P times, in parentheses, 1 plus R divided by N raised to the power of N times T, where FV is the future value of the deposit, P is the principal or amount of money deposited, R is the annual interest rate in decimal form, and number of times compounded per year, and T time in years. Solving compound interest problems. To solve compound interest problems, we need to take the given information and plug the information into the compound interest formula and solve for the missing value. The method used to solve the problem will depend on what we are trying to find. If we are solving for the time t, then we will need to use logarithms because the compound interest formula is an exponential equation, and solving exponential equations will, with different bases, require the use of logarithms. Now let's see an example. Let's solve a few compound interest problems. Example number 1. If you deposit $4,000 into an account paying 6% annual interest compounded quarterly, how much money will be in the account after 5 years? We simply use the formula. Let's see the formula again. Okay? P, which is the principal, here will be $4,000. the interest rate in decimal form is 0.06, which corresponds to 6%. And the number of times compounded per year here will be 4, because the interest is compounded quarterly 4 times in a year. And this 5 is the time in years. For us here, it is 5 years. Then we put on the formula $4,000, 1 plus 0.06 divided by 4, 4 times 5, which is going to be equal to 4,000 times 1.015 raised to the power of 20, and the final result is $5,387.42. Then, after 5 years, there will be $5,387.42 in the savings account. Let's see exercise number 2. If you deposit $6,500 in an account paying 8% annual interest compounded monthly, how much money will be in the account after 7 years? So the interest rate is 8%, but we are not going to use 8. We are going to use 0.08. As the interest is compounded monthly and there are 12 months in a year, then we are going to use 12 here. All right? And because it is 7 years, we are going to use 7 here. Then we conclude that the formula, the final value or the future value, will be 6,500 times 1 plus 0.08 divided by 12 raised to the power of 12 times 7. And this is equal to 6,500 times 1.006666 raised to the power of 84. And this gives the future value or the final value of $11,358.24. And we conclude that after 7 years, there will be $11,358.24 in the account. Now, let's go to example 3. How much money would you need to deposit today at 9% annual interest compounded monthly to have 12,000 in the account after 6 years? If your objective is to have $12,000 in your account after 6 years, how much money do you need to deposit? Then the future value, we already know, it is $12,000. And the principal is what we want to calculate. It is going to be 12,000 equal to P times 1 plus 0.09 divided by 12 raised to the power of 12 times 6. Remember that we don't use the number 9. We use 0.09. 12,000 is equal to P times 1.0075 raised to the power of 72. And this gives a final value of $7,007.08. You would need to deposit $7,007.08 to have $12,000 in 6 years. Now, let's see another example that's going to be related to this. If you deposit $5,000 in an account paying 6% annual interest compounded monthly, how long until there is $8,000 in the account? We are going to use the same formula, but now with a different objective. We want to know the time. $8,000 is going to be equal to $5,000 multiplying 1 plus 0.06 divided by 12 raised to the power of 12 times t. Why 12? Because it is compounded monthly in a year. Then in a year we have 12 months. And t we don't know because this is exactly what we are looking for. Then $8,000 is equal to $5,000 multiplying 1.005 raised to the power of 12 times t. And we pass $5,000 divided in $8,000, we get 1.6 equal to 1.005 raised to the power 12 times t. Now we can use logarithm to find the time. We're going to use the properties of logarithms. The logarithm of 1.6 is equal to the logarithm of 1.005 raised to the power of 12.t. Using the property of logarithm, we can pass this 12 times t multiplying as it is here. And then if we pass the log of 1.005 dividing the log of 1.6, we get this, okay? And then we're going to find that the time is approximately equal to 7.9. Very good. Congratulations. Now we know that it will take approximately 7.9 years for the account to go from $5,000 to $8,000. Let's see another example where we need to use logarithms. If you deposit $8,000 in an account paying 7% annual interest compounded quarterly, how long until there is $12,400 in the account? Now, we are not going to use the number 12. It is not monthly, it is quarterly. So there are 4 times, okay, the number of parcels. 12,400 is equal to 8,000 multiplying 1.007 divided by 4 raised to the power of 4 times t. T we don't know, we are looking for t. 12,400 is going to be equal to 8,000 multiplying 1.0175 raised to the power of 4t. 1.55 is equal to 1.0175 raised to the 4t. The logarithm, another time, we are going to use the property of logarithms, okay? The objective is to pass 4 times t to this side here. That's why we use logarithms. And using again this property, we find that t is equal to 6.3. And it will take approximately 6.3 years for the account to go from $8,000 to $12,400. Now let's see the last example, example 6. At 3% annual interest compounded monthly, how long will it take to double your money? At first glance, it might seem that this problem cannot be solved because we don't have enough information. It can be solved as long as you double whatever amount you start with. If we start with 100, then P is going to be 100 and the future value 200. So let's see. The problem wants us to, at 3% annual interest compounded monthly, we want to see how long will it take for the money to double. Okay, any kind of money. You could have used any kind of value here. Okay, we chose this, but we could have chosen any. 200 is going to be equal to 100 times 1 plus 0.03 divided by 12 raised to the power of 12 times t. 200 is equal to 100 times 1.0025 raised to the power of 12 times t. And then again, we are going to use that same property of logarithms to pass this 12 to this side here. And ultimately, we are going to find that the time is this. At 3% annual interest, it will take approximately 23.1 years to double your money. And now, I am going to finish this problem and this work that I'm bringing to you with additional problems for you to use in your studies. And if you are just remembering, try to practice using these problems here that I'm allowing you to see on the screen. Pause the video and then write the problems for you to practice solving. Okay, my friends, my name is Rafael. I am a teacher. If you want to book a lesson with me, just use my WhatsApp number. I am also a consultant. And if you want to have consultancies with me, use my number. Goodbye.